So welcome to this pre-recording of a lecture on symbolic numeric computing. So in this lecture we try to combine the best of both worlds. We can compute fast and accurate. For that we will be using interval arithmetic. I will motivate the use of interval arithmetic via the evaluation of an expression, and we will define yet another form of factorization, the symbolic or asymbolic numeric factorization. Since this lecture finishes a chapter called Calculus, I will end with a problem from multivariate calculus. The second part then makes the transition to the next chapter in the course, where we look at more the solvers. Okay, interval arithmetic. I will motivate this with this problem here. And the main question is in the title of this slide, how to decide on the level of precision. Here we have a motivating problem. We have an expression which I copied from a proceedings paper in SciPy 2008 conference. So this expression, we want to evaluate this expression. It's a polynomial, or almost. We see that we divide here. It's a polynomial of degree 8, not that high, but not that low either. And the numbers are 5-digit numbers. So the problem is small enough to have a nice exact solution, and we will start from this. But here are the questions. We've seen how to work with multi-precision arithmetic, but we haven't really addressed the question, how should you set the precision in order for the evaluation to be accurate. So here for this example, we know the exact value, and computing the exact value is also not a problem. But in most interesting cases, one does actually not know what is the exact value, or the exact value is too difficult or too simply not available. What one can then do is increase the precision and hope that when the result does not change much anymore, that then gives you a good impression, a good bound on the error. But for this example, as we will see, that gives that's not really correct. We will have, for several levels of precision, as we increase the digits, we will have plateaus of the same numbers. So the answer to this question is that we can compute with intervals, just like we can compute with numbers, and the size of the interval, so the interval contains the exact number, and the size of the interval gives us an error bound. So if these intervals are extremely wide, then in essence your precision is too low. Okay, factorization. So we look at a polynomial in one variable. A numerical or a numeric factorization is always computing all the complex roots, so essentially applying the fundamental theorem of algebra, as we have as many complex roots as the degree of the polynomial. It's a very nice result, but it can only be done numerically. Symbolic factorization starts from an exact factorization, so you factor first over the rational numbers, and then one adds sufficiently many algebraic numbers, sufficiently many formal roots, till you can write your polynomial as a product of linear factors. Now we can combine this, so the algebraic numbers, it starts to get really cumbersome after a while. Now the point is that we can combine this, so we can work symbolic numerically. So we are working with the imaginary unit I, so the symbol for the square root of -1. But then also our numbers are not really strictly numerical, but they are defined by intervals. And the intervals give us a bound on the accuracy of the roots. So this is asymbolic numeric factorization because it depends not only on the order of the roots, but it depends on the level of precision that we are using. Okay, so then the last topic that I would like to illustrate is the use of a solver. So we will make the transition to a new chapter where we will solve polynomial equations, differential equations, linear equations, and look over polyhedral optimization. Here is a very general problem. We have a blue sphere, or a sphere drawn in blue here, and we want to find the points on the sphere for which a given function is optimal. So here is the geometric representation of this problem. The sphere is drawn in blue, so this is the constraint. All our points, the points that we consider, have to satisfy the equation for the sphere. And we are evaluating, in some sense, all the points at the target, the function f, drawn in red. So here we have one level set. So these are all the points where the function, I think, has the value 2, has a specific value 2. Okay, so how do we solve this? Well, at a critical point, as at a candidate minimum or maximum, then the gradient of the target is parallel to the gradient of the constraint. So we have defined gradients before, so this is the vector of all partial derivatives. And we can compute these gradients very quickly. And the condition of the gradients parallel to each other is expressed via a multiplier, which is indicated by this Greek letter lambda. So lambda expresses here, so the first equation, which is actually a sequence of 3 equations. So this first equation here, it's a vector equation, expresses that the gradient is a multiple of the gradient of the constraint is a multiple of the gradient of the target. And we solve this system augmented with the constraint on the gradient. So we want to find all the points that satisfy the constraint, in our example, points that lie on this sphere, and that for which the gradients are parallel to each other. So this is a geometric problem that translates very nicely into a system of polynomial equations, which we can solve rather quickly with SageMath. Okay, so let us then go to SageMath. So I will swap the slides for the notebook. So I have a notebook prepared, but I will type in the expressions anyway. So this is lecture 25 already. So in this lecture 25, in the summer of 2022, we consider symbolic-numeric computing, trying to combine the best of both worlds. We can compute accurately and efficiently. And we will introduce interval arithmetic. So interval arithmetic is useful in that it provides us with bounds on the errors of our calculation. So with interval arithmetic, we compute bounds on the errors. I will use the example of Stefano Taccini from the SciPy 2008 proceedings. The SciPy conference, by the way, takes place in Austin and has taken place or is taking place in this month. All right, I will copy the expression because I will make typos, and it's actually not so interesting to see me making type errors. So this is an exact expression. So I have, so the original expression is with decimals. So there are two decimals in there, but I have, so this 5.5, but they are converted into rationals. To be very strict, if we are going to do our approximate computations, we should also no longer work with the rationals, but what will happen automatically is that the rationals will be approximated during the computation. So the computation in SageMath will still in some sense be very much hybrid. So let me copy also the other cell. So that's the last copy and paste that I will do. So this defines the setup. So here we have our exact calculation. So this is our reference. Now what is the problem? Find the precision needed to obtain an accurate result. So let me first see what is the exact, what is an approximation. So I can take this rational number and evaluate it to 8 decimal places. So suppose that we want 8 decimal places, then we need to find something that starts with minus 0.82. Okay, so let's do our first numerical approximation. So you see I used the .n, so the n method on an exact number. So the two exact numbers that I have there are a, so let me do digits equals 8, and bn digits equals 8 as well. So what do we see? So what if we, so the sequel course is numerical analysis, and what we do in numerical analysis, if we want 8 decimal places, we're also going to compute with 8 decimal places. So a numerical analyst would immediately say that this is an ill-conditioned result regarding the single floats. And I will make the observation. So observe that the number is really huge. So we have minus 1.5, so it's a very negative number, but it's 10 to the power 27. So just in case we did not notice the scientific notation, so here it is. So very, very far. So what can we do then? Well, let me make a list now. So we started at 8. So let us make a list of floating point evaluations starting at 10 and ending at 40 decimal places. So this is to simulate what one would do. One would gradually increase the precision and stop whenever the process converges. So we'll evaluate the arguments for a parameter k. For k in the range 10 to 41. And you see that even at 10 decimal places, I get 10 to the power 25. It gradually goes down. But you see we have our first plateau, first consecutive, the same values here with 10 to the power 18. But then if we would go one step further, we would see that it drops even more to 10 to the power 17. So I should actually show the entire sequence. So here what is very troubling is the plateau at -2. So you could say, well, we have to compare 3 consecutive values for 3 increasing values of the decimal places. But then here we have another, well, no, I'm sorry. So there is 6.11, but there is a drop here from 10 to the power 12 to 10 to the power 10. But what is really troubling is the plateau at -2. So there we have 4 or 5 consecutive values that are the same. So one could decide, well, just stop there. But that would give to a completely wrong result. And you see that as we approach 40, so the last number is 40, so 39, 38, 37. So one needs at least 37 decimal places to get a correct result. With this expression where we are using the exact rationals. So the outcome here, so let me emphasize this by documenting. So we see that evaluation at increasing levels of precision, that evaluating at increasing levels of precision actually gives wrong confidence. May give false results.
Here are some results from a search.
So, interval arithmetic. So we have the real interval field. that is predefined. So we had the RR. We also have the RIF. So the RIF is the abbreviation for the real interval field. So by default, it is with 53 bits of precision, which corresponds to the standard double float. So what you see is that when I do this, the result looks rather strange, but observe the exponent. Observe also that I can assign this. Perhaps I should have done this already. So let me change the cell. So it's always good to check the type. So it is a symbolic expression, but we can coerce this into a real interval field, and I can ask to show this with the bracketing notation. So this is the long format. Observe that our interval is extremely wide. So in some sense this is a pointless result. The interval is very wide. So let me typeset it in LaTeX to have the scientific notation. So this is an interval between negative 10 to the power 21 and plus 10 to the power 21. So the point is it's entirely wrong, but we have an estimate also for the errors. So we could also ask to compute. So I think that is the diameter that we can ask. So this gives actually the errors. So you see now that we can systematically increase the precision and each time compute the diameter, which is the upper limit. So here are some useful attributes. So I have the upper limit minus the lower limit. I think it might be the lower bound and I will on the upper bound. Okay, so then I have to check my preparation here. So it's just upper and lower. So this gives the same as the diameter. Okay, let me double the precision. So I'm going to work with a real interval field of 100 bits. Evaluating the function in that precision is accomplished by converting the arguments, and then so the outcome is an expression, and I have to print this to see the error with the brackets. You see that with 100 bits, the precision is still, the accuracy is extremely bad still. We have a wide interval between -4 to the power 10 to the 6 and 10 to the 7. So we have really huge bounds. So let me do this one doubling of the precision one more time to 200. So the y200 is the result obtained by computing in that precision. And now you see that with 200 bits of precision, actually I do get quite an accurate result. The diameter will tell how many decimal places in the result are correct. So we see there are about 24 as the diameter of the interval is 10 to the power minus 24. We have about 24 decimal places correct in the answer. And that can also be seen from the expression. So just count the number of digits until the question mark. Okay, so this is the interval arithmetic. So we compute with intervals so that we could, in similar fashion as we compute with numbers. The arithmetic is a little bit more expensive, but it has the benefit of providing a bound on the error. And if the process is converging, then we have guarantees on the accuracy. So this is often also referred to as rigorous computing. A related topic is the factorization. So a numeric factorization of a polynomial p in one variable computes the roots over the complex numbers. So essentially applying the fundamental theorem of calculus. So in a symbolic factorization, we add to the field of rational numbers sufficiently many algebraic roots. Till the polynomial factors. So a symbolic numeric factorization works in SageMath over QQ bar. So QQ bar is a hybrid. It's an extension of the rational numbers with the symbol I. So in a way it also uses the letter I, but it uses interval arithmetic numbers. So I will define a polynomial ring in X with coefficients in Q bar. So any expression, polynomial ring, so any expression that I'm typing in X now will be a polynomial over this QQ bar. And you can see it's over an algebraic field. So let me type in a polynomial. A polynomial that essentially does not factor over the rationals. And here is the factorization, where I could have also computed, so there is the complex interval field, abbreviated as CIF. If I ask SageMath for the roots over this field, then you see that the factorization that was computed, or is indeed a factorization with respect to the 53 bits of precision, that this corresponds to one real root and two complex conjugated roots. So the roots are listed as tuples with the second field in every tuple the multiplicity. So all roots appear only once with multiplicity 1. So I can get the factors out of there. So if I want to see the list, so here you see the list of the factors. So you can also compute. So if I want to see the factors with 200 decimal places, a more accurate symbolic numeric factorization, then we ask for the roots over a complex interval field of a higher precision. So let me illustrate this. So let me make a field of 200 bits. And if I'm asking now for the roots, then you see that I get the roots with the 200 bits. If I want to only see 10 bits, then I can also do that. I can select the roots. So let me do this. So I will make the capital R. So this is the list of tuples. So from the list of tuples, I will select the roots. So in the list comprehension, I'm splitting off the multiplicity. So this gives me the multiplicity removed. So now I have a list of numbers, and I can use the product of x minus r so this is still a list comprehension, but that list comprehension is given the list comprehension is given to the argument of the product. You see that the product automatically expands, which is not so good here. Or on the other hand, it is an indication that there is not going to be any expression swell. And in some sense, there is an interpretation. We see that, so the automatic expansion of the product is justified because of no expression swell. So we start with a list of here 3 roots, and we're going to end with 3 coefficients. And the coefficients are actually getting smaller. So you see that we had no quadratic term. So you see the working precision is about 59 decimal places. What we see is what is called in numerical analysis, we see the backward error. So the backward error is we computed numerically at quite a high precision already of the results. So this backward error is the exact polynomial for which the computed roots are the roots. So this is a nearby polynomial nearby the x to the power 3 plus x plus 1. So what is this backward error here? We see a nearby polynomial near the x to the power 3 plus x plus 1. Okay, a symbolic numeric computation, a symbolic numeric factorization, in addition to the symbolic factorization with the formal roots and the numerical factorization over the complex roots. So this symbolic numeric factorization has still a geometric interpretation, but also comes with guarantees on the accuracy. Okay, so the last topic to conclude and to transition into the next chapter is on constraint optimization. So in this next chapter we're going to solve polynomial equations, linear equations, differential equations, and optimize over polyhedra. I will go to my preparation to get the problem formulation correct. So here is our problem. The constraint is a sphere, x squared plus y squared plus z squared minus 1. So this is our equation. And we want to optimize the target for this. So this is our problem. Let me try to visualize this. So I have a plot of the sphere. So I will plot with implicit plot 3D the constraint for x. Oops. And perhaps I should have copied and pasted, or at least perhaps I should copy and paste, because there are some issues which I may not have correct right away. So notice that the constraint is given by an equation. So here is a nice viewpoint. What I want to indicate is that the sphere does not touch the sheets. So I have the target. The target is a function in 3 variables. I can't really plot this in full generality, so I pick a value. So I'm picking, so the implicit plot plots an equation. So I'm having the target minus 2 equals 0. So this also gives me an upper bound on the optimal value. So for all the points on this blue sphere here, I cannot reach the target. So there is no value where there's no point on the sphere, on the blue sphere, for which the target will meet. So let me simply adjust this now. So this is the nice thing about the dynamic setup. So this is a concocted, very simple problem. So for the target equal 1, you see that the blue sphere touches the sheet, and it touches the sheet at 2 points. So I have my blue sphere, which is now wedged in between these 2 sheets. So I have 2 maximal values, so 2 points on the sphere for which the target will reach 1. So this is a geometric interpretation of this problem. So again, this problem is defined very nicely, taken from a calculus book, so that there is a very nice formal solution. Okay, so how do we solve this now? We have to compute the gradient. So I have my expression for the target, and I'm going to turn the target into a function. And I can do this simply by setting the expression equal to target. So why am I doing this? Well, I have the gradient of the target, so I call this GT, and this gradient can be computed very directly. So this gives me the vector of, or the tuple of, the three partial derivatives. The alternative is to use a list comprehension if you work on the expression that is stored in target. So I'm going to do the same with the constraint. So I have the function for the constraint. So I'm taking the left hand side of the constraint, because the constraint was defined by an equation. And also here I have the gradient of the constraint defined by taking the function and applying the diff method to this. So let me describe what I've just done. So in FC we have the function that defines the gradient. In GC we have the gradient of the constraint. So the gradient of the target and the gradient of the constraint. So that's the first step. So this has a three-step process. So it's the first step in setting up the problem, computing the gradients. Then we apply the technique of the Lagrange multipliers. I will use W for the lambda in the Lagrange multiplier method. So using lambda is not a good method, not a good symbol. So I have my expression for the gradient, and I will subtract from it the expression or the function. So I have the functions and I will turn them into expressions. So, and that will be, let's assign this to equations. And here you see the problem. I can't really do this because there are vectors. So I have to select the components. So for k in range 3, and that still is not working. So what do I have? I worked too fast, so let me see what happens if I'm evaluating the gradient. Okay, so I had to take the gradient of the target and there I can select the kth component from, and I have to select the gradient of the constraint, but seen as expressions. And that will give me the first 3 equations in the system. Almost done with step 2. I have to add the constraint to it. And the constraint was here defined as an equation. So I have to append the x squared plus y squared plus z squared minus 1, the equation of the and I'm almost done, but I forgot the w. You see, I was about to say I have a system of 4 equations and 4 unknowns, but I was observing just before I was going to solve this that there was a letter missing. So here is now the system, and I can solve this system, the equations for x, y, and z, and the Lagrange multiplier. Okay, and that is almost it. So I still have about 4 minutes to interpret the results. So which are now the minima and which are the maxima? So I have 6 critical points where the gradients are parallel to each other. I have to evaluate this at the target. So we have to evaluate this at the target. I have a lists of equations. So for every solution, I have to select the left-hand side. So how am I doing this? So I'm going to select for the right-hand side. So for every equation in the solution, for every solution in the list of solves. So this gives me the coordinates, but the coordinates are still listed with this W. I'm actually not interested in this W, so I have to drop the W. So how I'm going to do this? So let me make another list comprehension. So I have now this list. So this is a list of lists still. So I'm going to turn this into a list of tuples. So where I'm going to take the x, the y, and the z for x, y, z, w in E, and let me convert the E to a tuple for every E in L. Okay, so this is an interesting exercise because I wanted to do too many things at once. So for E in L, which gives me a list, so I have a tuple which I cannot unpack. So let me keep it then for any item. So I'm in E, and let me do then the simple selection where I select there are things now wrong with the brackets. So this is a list, and I should be able to select the first arguments, which is not subscriptable. So everything is expression. So I have to convert to a tuple to make it subscriptable. Okay, so this is starting to get very annoying. I prepared this, so let me copy and paste. So here we have the correct solution. So I can convert everything to a tuple. I have made the mistake that I have the E is already a list. And I could have done simply the selection here. So a simple list comprehension will do this. So now I have the coordinates in T, and I can evaluate my function in the target at the elements of the tuple. If they are actually tuples, and they are. So you see now I'm running over time, so I'm sorry about all the struggles. We see that we have 3 maxima with value equal to 1, and we have 2 maxima and 2 minima with value equal to -1. So going back to the points, so the first 2 points, 1, 0, 0, -1, 0, 0, they are the 2 maxima, and the next 2 values are in the list. So here you see the list for -1 for z, +1 for z, we have minima. Okay, in my preparation, when I was doing this with copy and pasting, I needed 29 instructions. That notebook will be posted. Here you see if I'm trying to explain this and get distracted by all kinds of things, that it takes me 63 instructions. So I hope nevertheless that this was interesting, despite me going over time. So let me emphasize again the solving, the setting up of the solver, and the geometric interpretation. So the third section in this notebook is kind of a preview of the next chapter that is to come on solving problems. We concluded the calculus chapter with a symbolic numeric factorization and using the interval arithmetic, which gives us a way to compute automatically with arithmetic the error bounds, which leads to rigorous computing. Thank you for watching.